Okay, so today we're going to think about the energy dissipation in a circuit. So we said before that it took some work to push a current through a conductor. So let's think about how much work that is. So in a time dt, it takes, if we have a current I passing through from one side to the other, then in a time dt, an amount of charge, I dt, should move through. So that means an amount of charge dq passes in one end and passes out the other. It's not the same charge, but that's the net change for that element. Now the initial potential energy of the charge going in is the amount of charge times the potential, so the voltage at the left end. So we'll call that V high because it's at a higher potential. While the potential energy at the other end is the same charge times the potential at that end. So that we can find the change in the potential is just the charge times the difference in potential from one end to the other. Okay, so if we call V the potential difference across high minus low, we see that the change of potential energy is negative the amount of charge times V. It's important that we always remember, even though it doesn't say delta V, that when you talk about a circuit element, V is the potential difference from one end to the other. Okay, so re-expressing that in terms of the current, and then dividing by the time interval, we see the rate of change of the potential energy is negative I times V. So apparently I times V is the rate at which energy is dissipated in the element. Okay, so the change in the potential energy is the rate at which you're losing, since there's a minus there, is the rate at which you're losing energy. So let's do an example. So suppose you have a toaster. A toaster is essentially a piece of semi-conductive wire held close to the bread with a large current through it. So let's think about a toaster. It's plugged into a 120 volt circuit. Toaster says it's 500 watts. We've measured all the wire in there and we figure out that there's a length of 2 meters of wire in the whole toaster. I'm just showing it on one side of the toast, so there'd be at least three more of those. And so the question is, what's the radius of the wire that we should use in order for this to work? Okay, to get this much power with this much voltage. All right, so that's the goal. I've given here the conductivity of the nichrome. Okay, so first we know we can use Ohm's law on this material. So if we know the voltage difference from one end of the wire to the other, we can from that calculate the current. Okay, so solving Ohm's law for the current, we find that it's the voltage divided by the resistance. Of course, we don't know what the resistance is, but we do know that the resistance should depend on the geometry of the wire. So that's our in here. So re-expressing the power now, which we also know, which is the current times the voltage, we can write that using this guy here as V squared over R. So solving that for the resistance, we find it must be the square of the voltage divided by the power, and we know both of those, so we can compute the resistance of the wire. And then we bring up our rule for how to calculate resistance for a wire. It's the length divided by the cross-sectional area and the conductivity. So since we know the resistance and we're trying to find the radius, let's find the area first. So we solve for the area. And we can calculate that. But the area we know is pi r squared. So from that, we can find the radius. Okay. So like 1/5 of a millimeter. All right, so the main point here was, is this guy. We've been practicing Ohm's law, but we have a new equation here. It's very important. It's very general, okay? Power is always current times the voltage in a circuit. Remember, with the voltage being the difference across the ends and the current passing through the element. Okay, so the thing is, I just lied to you. The voltage on the toaster isn't 120, and even though all your appliances say 120, the voltage is not really 120 in the outlet. It's actually 170, and then it drops down to minus 170. It's an alternating current, or an alternating voltage. We usually call it AC. I don't know why. Just we say alternating current. Of course, the voltage alternates too. Okay, so that's the actual signal. It's oscillating from 170 to negative 170 at 60 times a second. So why do we say that it's 120? Why this seems like kind of a crazy thing to do, because it's almost never 120. Okay, well, let's go back to our calculation of power. We saw that we could express the power as 1 over the resistance times the square of the voltage. Now, if we graph the square of the voltage, we see that it also oscillates, of course, but it doesn't oscillate about 0. It oscillates about the midpoint. Okay, so you might recall some formulas about trig functions that if you square it, obviously it can't be negative anymore, but you actually get a trig function back. So and we won't go into that because it's not relevant, but you get a displaced trig function. And so it oscillates about the average value, which is just the midpoint. So midpoint between 0 and the maximum voltage squared. Okay, and so the average power, so the power in the circuit is going to be oscillating as 1 over R times V squared. So if V squared oscillates, the power oscillates. But the average power, the time average, will just be related to that average voltage, which is this average square voltage, which is just that midpoint there. So a little bit of magic of math here. We write that out in terms of the function. We can take the constant out in front. And then we know actually that the average of cosine squared is 1/2. So that's really nice, makes it easy. I'm going to rewrite this in a slightly strange way, but we're going to see in a second where the 120 came from. So I just put that 1/2 inside the square root, so it becomes I put the 1/2 inside the square, so we have to have a square root inside. But if you put our value of 170 volts in there and divide it by the square root of 2, you get 120. So that's the reason that we say that the outlet is pumping 120 volts, because it makes this calculation easier. So this is like the original formula. The power is 1 over the resistance times the square of the voltage. If we'd used 170, we would have got the wrong answer for the average power. That would have been the peak power. And what you're really concerned with is the average power applied to your toast. So this is almost always the relevant number. Okay, So if you're worried about the wires in your house overheating because you have too much power being dissipated in them, what matters is the average power. This is again an RMS value. If you think about it, what was that 120? Well, that was the square root of the average of V squared. Okay, so that's V RMS. So in some sense, applying a constant voltage of 120 volts is the same as applying an oscillating voltage that goes from 170 down to negative 170. It does the same amount of work on average. So using 120 volts allows us to ignore the oscillation when computing power.